Good afternoon, Professor Jack Dongarra, Professor Wei Kuo, colleagues, students, academic friends, ladies and gentlemen. We appreciate you taking the time off your busy schedules and being with us here today attending Wei Kuo lecture on an overview of high-performance computing and future requirements. At this moment, may we invite Professor Raymond Chan, Dean, College of Science, onto the stage for his introduction and opening remarks. Professor Chan, please.
Good afternoon. Welcome to the inaugural lecture of the Wei Kuo Distinguished Lecture Series. We named it in May 2023 in honor of Professor Wei Kuo, outstanding achievements and contributions during his 15-year presidency. Though this is the first lecture of the renamed series, it is based on CTU's long-standing Distinguished Lecture Series, which will continue to serve as the platform for the university community to listen to, meet, and talk with distinguished speakers and interact with their academic counterparts from other educational and research institutions. Its content will be technical in nature, and its style of presentation modeled on an academic lecture or conference paper. Today's lecture by Professor Jack Dongarra reflects on the past and present of supercomputing and prognosticating the future directions of this field. In a fast-changing world, supercomputers play a crucial role in rapidly processing data to yield actionable results. They facilitate breakthrough technologies that have the potential to transform the world. Through supercomputing, we witness the most significant technological advances of our day, spanning astronomy, weather and climate forecasting, material sciences and engineering, molecular modeling, genomics, neurology, geoscience, and finance, all accompanied by numerous success stories. Perhaps there is no one suitable to discuss the topic than Professor Jack Dongarra, a respected computer scientist who has dedicated 5 decades to align the algorithmic characteristics of mathematical concepts with the practicalities of hardware. Professor Dongarra holds the title of Emeritus Professor and Research Professor at the University of Tennessee, and also has appointment with the Oak Ridge National Laboratory and the University of Manchester. He has been actively involved since the origin and formation of the top 500 supercomputer list in 1993, which used his LINPACK benchmark as the common applications for evaluating the performance of supercomputers. When Professor Dongarra was honored with the 2021 Turing Awards by the ACM, the Association for Computing Machineries, he received acclaim for his outstanding contributions. The ACM praised him for establishing a framework that has empowered scientists and engineers to make significant discoveries and groundbreaking innovations in diverse areas such as big data analytics, healthcare, renewable energy, weather prediction, and economics. Therefore, we are extremely delighted and honored to have Professor Jack Dongarra here today, not only to look into the past and present of supercomputing, but also its future directions and prospects. I'm sure it is going to be an exciting journey. I will now leave the stage to Professor Jack Dongarra. Thank you.
Thank you, Professor Chan, for those enlightening words. Now, for the focal point of our gathering, rather, it is an honor to introduce Professor Jack Dongarra, a supercomputer guru and a Turing Award laureate, currently serving as Professor Emeritus and Research Professor in the Min Kao Department of Electrical Engineering and Computer Science at the University of Tennessee. Professor Dongarra, please.
Well, thank you so much for that kind introduction. It's a pleasure to be here with you today. When Wei asked me to come and speak at this inaugural lecture series, I of course immediately said yes. Wei was my boss at the University of Tennessee for many years, and I had no other choice but to say yes. But it's a pleasure to be here with you today. So we're going to take a look at high-performance computing and see where things are today and maybe where things are going to go into the future. So, we have a changing world. You know the story as well as I do. Computers really pervade all aspects of our society today. It has implications for e-commerce and business, research and development. And we know companies like Apple, Samsung, Google, and Huawei really dominate the world of smartphones. I have a laptop here which just has an incredible power associated with it. It has that M2 chip in it. It has 15 trillion transistors equivalent. It has 8 cores. It has 10 cores GPU. And I use this device mainly to read email. So it's just an incredible tool that we have at our disposal. We have companies like Google, Microsoft, Amazon, and Apple that have this incredible dominance in terms of their value. Each of those companies have a market value equivalent of over $1 trillion. That's an incredible situation that we have today. And not far behind are companies like Baidu, Alibaba, Tencent. And all of those companies are designing their own silicon. So they're not using commodity processors. They're going off and designing their own processors that can be used in their cloud services. If we take a look at the market capitalization, we see that these companies here have that over $1 trillion market capitalization. They're worth over $1 trillion. And if you take a look at more traditional computing companies and you add up their capitalization, it only comes to $1 trillion. The aggregate comes to $1 trillion. So we have an incredible situation in terms of the worth of these companies here. One exception is NVIDIA. So NVIDIA is a company that makes GPUs, and they're used in many ways in scientific computing, and more recently, of course, they've been used in machine learning and artificial intelligence. And that company, NVIDIA, has a market capitalization as well of over $1 trillion. So very impressive situation. So these companies are designing their own silicon, their own hardware. Alibaba has their CIPUs that they're using with 128 cores that they designed. Amazon has their Gravitons. Google has their TPUs. Microsoft has their own chips that they're using to drive their cloud services. And even car companies are in the act. So even Tesla has designed their own chips that are being used in their products. So they're not using commodity processors. That's an important aspect. They're designing things that are specialized for their needs. They have that enormous wealth that they could do that investment in designing their own chips, as opposed to us in the scientific computing area where we don't have that access to be able to design our own chips. We're forced to using commodity processors for the most part. So we have a list that's called the top 500. The top 500 lists the 500 fastest computers, and that list comes out twice a year. And I'll make reference to it as we go through this talk. When we started this list back in 1993, so it's 30 years old, there were 65 systems that used Intel processors. And most of the supercomputers were designed by these companies here. So these companies like IBM, Cray, SGI, Thinking Machines, and then the Japanese companies NEC, Fujitsu, and Hitachi. At that time, we had vector computing. Vector computing was the way in which most scientific computing was done. And only a few machines, so we're looking at, in this graph here, we're looking at, his pointer seems to be missing. We're looking at time and looking at the number of machines that are on the top 500. And I've highlighted here the Intel machines and the AMD machines that were on the top 500 back between 1993 and 2003. So just a small fraction. But something happened around 2004 that changed this story. So in 2004, we had this attack of the killer micros. So microprocessors became much more powerful, and they were commodity processors, and they were integrated to design and build parallel systems that had tremendous computational power. And we saw that Intel processors, the x86 architecture, the instruction set that drives Intel and AMD, really dominates high-performance computing from roughly that point in 2004 until today. So most of the high-performance machines that are on the top 500 list are using x86 architecture to drive them. And 97% of the systems today use that instruction set. And those companies that built those early supercomputers, most of those companies are no longer either in business, and they're certainly no longer putting machines into the high-performance computing market. Some of the companies like NEC, Fujitsu, and Hitachi still make machines which show up on the top 500 list. And most of the machines use GPUs. So if we take a look, using the top 500 list again, if we take a look at the frequency of the processors that are used in the top 500 list, we get a story that looks something like this. So the frequency, the rate of execution or issuing of instructions, started out to be something on the order of 100 megahertz in terms of the frequency of the processors. And we saw that rise quite rapidly until roughly 2006. And then it became stable, right? The frequency hasn't changed much since that time. So what happened around that time that halted the frequency increase? Well, what happened was something called the ending of Dennard scaling. So Robert Dennard is a scientist at IBM Watson Research, and he wrote a paper a number of years ago which talked about this scaling effect. He says as the dimension of the device goes down, so we're going to shrink the device, so does the power consumption. So smaller transistors ran faster and used less power and cost less. That was Dennard scaling. So in the old days, when I had a computer and I replaced it with a new computer, and Dennard scaling was in effect, my applications ran faster on that new computer because the frequency was faster. So I got a benefit just because of the frequency. I didn't have to do anything. But something changed about that time. So we no longer got the advantage of the frequency. And what happened as a result of that is that parallel processing came into effect. So now, when I got a new computer, I couldn't rely on the frequency change. I had to do something. As a programmer, person who writes software and applications, I had to change what I did to implement things in terms of parallel processing. So that was the only way to get the advantage of those new machines. So smaller devices, and the reason for this Dennard scaling failing is that the smaller devices, the Moore's law is increasing, and we get this thinning of the dielectrics that occur on the chip, and shorter channels that lead to voltage leakage, and that voltage leakage turns out to heat up the chip. So there's a formula that goes something like this. The power required for the chips is proportional to the voltage squared times the frequency. And the frequency and voltage have a relationship, so that the power goes something like the frequency cubed. So what that says is if I double the frequency, make it twice as fast, I need 8 times more power to make that device go. And I can't support that. So today's chips are 3 gigahertz, and that chip is about 100 watts. So that's what we get from our desk-side machines. So think about a desk-side machine with 800 watts. You really can't have that in the area of about your fingernail having 800 watts. You couldn't have the cooling associated with it to make that work. So Dennard scaling was a big deal. It ended, and that made many things change along the way. So if we take a look at the performance per core, again, based on the top 500, we get this steady increase that's happened over time, and that's still happening today, the performance per core. And if we take a look at the performance per socket, so now we have the performance per core. Today we have multi-core, so there are many cores on a chip. And if we take a look at the performance per socket, we see that increasing, still increasing at a much higher rate. So something is driving that, and what's driving it is the use of GPUs. So GPUs came into the scene about this time. GPUs provide much more computational ability, and that computational ability is giving us more performance on that individual socket or chip that we're using today. So today we have a situation where NVIDIA really dominates the use of these graphical processing units in our supercomputing. And you can see that over time, what's happened here. The time situation is such that, this pointer here is not quite working as I hope. We see the dominance occurring here with roughly in 2012, these accelerators were starting to be used in our supercomputers, and today we have a situation where roughly more than half of the performance that we see in our supercomputers is coming from the use of these graphical accelerators, and NVIDIA dominates the story here. And the other thing that happens is the interconnects that we use to make our parallel machines, we're using commodity interconnects for the most part. Those commodity interconnects are coming from gigabit Ethernet and also InfiniBand, which are off-the-shelf products. So the high-performance computing in terms of the scientific area is being driven by commodity processors, commodity interconnect. And oh yeah, by the way, everything is based on Linux, so we have a commodity operating system as well that's driving this area. So the US Department of Energy is a big investor in high-performance computing. Today, science is really driven by simulation, and the Department of Energy is investing heavily in terms of high-performance computing. They invested $4 billion over the last 7 years. So what do you get for $4 billion? Well, you get 3 supercomputers. So these supercomputers are roughly $600 million each. That's for the hardware. And the first one is in place and running at Oak Ridge National Laboratory. So that's a computer called Frontier. It has AMD parts in it. So AMD CPUs and AMD GPUs in it. And I'll talk more about that in a moment. The second machine is being installed at Argonne National Lab outside of Chicago. And that machine is based on Intel parts. Intel CPUs and Intel GPUs are going to be in that machine. It's not quite up and running today. Part of it is, not all of it. And the third machine is going to Lawrence Livermore National Laboratory. And that machine is called El Capitan, and it's based on AMD parts, the next generation of CPUs and GPUs that AMD is producing. And that machine is not yet up and running. In addition to that, there are 21 applications that have been specified. So this program is really about those applications. So the 21 applications are all energy related, dealing with things like wind energy, dealing with genomics, dealing with proton science. The list goes on, materials, fusion, astrophysics. Those are all applications that are being developed that have a need for high-performance computing, and these computers are going to be used to help advance the research as going forward. In addition to that, there are 84 software projects that are put in place to develop software that are needed by those applications to drive those applications on those high-performance computers. So that was a project that was started 7 years ago. It's about to end. In fact, it ends at the end of this month. What I mean by that is the money goes away at the end of this month. So this project here will end. There are 800 people working on this project, developing the applications and the software. And there's no follow-on project. I find this to be an incredible lack of foresight on the part of the Department of Energy, where 800 very talented people are working on this project, and the funding is about to run out, and there's nothing after this project to absorb them. So today's high-performance computing environment looks like this. It's based on a highly parallel system. That parallel system uses distributed memory, and the programming paradigm that we use is something called MPI, Message Passing Interface, plus OpenMP. The MPI part is used to communicate between the nodes of the system, and OpenMP is used to do the programming within a node. So basically, you write a Fortran C or C++ program, you make calls to MPI and OpenMP in your program, and you try to orchestrate things running on these high-performance machines. The number one computer is listed there. It's the Frontier system, and it has 8.8 million cores. So if you're going to program this machine at scale, you have to orchestrate that number of processing units on the machine. And most of the power comes from the GPU. 98% of the performance is going to be extracted by the GPU alone. So you had better be using that GPU on your application, or you'll see very little performance. So we have a heterogeneous environment, commodity processors, plus these accelerators. We have a situation where communication is very expensive on these computers. So these computers have been over-provisioned, I think, for floating point arithmetic. There's too much floating point capacity there. But what's lacking is the ability to move information around the machine. So moving information is critical, getting data to the right parts, organizing things so that we minimize the communication is critical for having a well-run application. And that's something that's quite different. And in fact, in the old days, when I had two algorithms that did basically the same thing, I would choose the algorithm that had less computation associated with it, because it was going to run faster. But today, that's not the case. Because of the communication that's associated with the algorithm, that has to be taken into effect, and communication is so expensive that it will really dominate the overall time to solution. So the amount of computation or work is essentially driven not by the floating point capabilities of your application, but by the communication trends. And today's hardware comes in different flavors. So we usually think of scientific computing working in 64-bit floating point arithmetic. You could also do 32-bit. But today's machines have the ability to do 16-bit floating point arithmetic. Now that 16-bit floating point arithmetic was not there for doing scientific computing. It was put there for doing machine learning. The machine learning applications can get by with very short precision. In fact, some machine learning applications can get by with 8-bit floating point arithmetic. I'm not sure how I could use 8-bit in many of the calculations I do. So we're going to be talking about fast computers. The fastest computer is an exaflop computer. Exaflop. So what's an exaflop? Well, let's start with a flop. So a floating point operation is an add or a multiply. And in this context, I'm talking about 64-bit adds and multiplies. Adding two numbers together, getting a 64-bit result, multiplying two numbers together, getting a 64-bit result. That's one flop in this context. An exaflop is a billion floating point operations per second, 10 to the 18 operations per second. I have a hard time getting my hands around that. I gave this talk a few months ago. There was a reporter in the audience, and afterward he came up and we talked about the high-performance computing. I said a billion, and he wrote a story. I read the story the next day, and he said 2 billion. This is not 2 billion. This is a billion operations per second. So this is an incredible 10 to the 18 operations per second. So think of it like this. Again, if each person on Earth, everybody, did one operation per second, it would take 4 years to do 10 to the 18 operations. 4 years at one operation per second. At the University of Tennessee, we have a stadium, a football stadium, American football. This is like a cathedral. It has 100,000 seats in it, and it's used only 6 days a year. And that stadium is full. So think of it like this. If we gave everybody a laptop like my laptop here, each person in the stadium, 100,000 laptops, and connected them together, that would give us 50 petaflops of computing power. So what do we need to get to an exaflop? How many stadiums full of people with computers do we need to get to an exaflop? We need 20 stadiums of people tied together with laptops to equal that one exaflop computer. Now, it makes no sense at all to do what I just said, having all these machines together, but again, just to give you an idea of the power of this. I became an accidental benchmarker a number of years ago. So I was involved in a project called LINPACK. LINPACK was a project to develop mathematical software, to develop software for solving systems of linear equations, AX equal B. And that project was an NSF-funded project. It involved 4 groups, one at Argonne National Lab, one at the University of California, San Diego, University of Maryland, and University of New Mexico. So this picture here gives Jim Bunch from San Diego, Pete Stewart from Maryland, Cleve Moeller from New Mexico, and that's a picture of me, a 1979 version of me with a little bit more hair. And that's my car. That's my car with the LINPACK license plate. So we produced this package of software called LINPACK, and in the appendix to that user's guide, I put together a little table of about 20-some machines and listing the performance, running that software on those 20-some machines. And I ranked the machines, and that was in the appendix, and the table looks something like this. I hand wrote the megaflop rate. So you could see the megaflop rate of the different computers. The fastest computer was a machine at the National Center for Atmospheric Research in Boulder. It ran at 14 megaflops. That was the rate for solving that system of equations. And today, this list has grown. I had a colleague at the University of Mannheim, Hans Moyer. Hans Moyer had a list of the fastest computers, and he ranked them by the theoretical peak performance. I had a benchmark. And Hans came to me and said, we should merge our two lists and call it the top 500. That was back in 1993. So we started this list back in 1993 with listing the 500 most powerful computers solving that problem. A matrix problem, AX equals B. It's a dense matrix problem. So I think about a matrix full of numbers, all of them non-zero. You're going to solve it using Gaussian elimination with partial pivoting. That was the method that was used in LINPACK. That's the method I first learned in high school for solving systems of linear equations. And that's the ground rules for running this benchmark, is to use that algorithm. You can implement it as best you can on your computer, but you must use that algorithm. And you have to get the results correct up to 64-bit precision. So you have to use what we would consider to be double precision on these machines. And we maintain this list that comes out twice a year. It's more of a hobby for me than anything else, the list of the top 500. And this is a snapshot, if you will, of the results from the top 500 since it began until today. So what we're looking at here is over time. So this is back in 1993. The red line is the fastest computer. And the blue line is charting the machine at position number 500. So that's the guy at the bottom of the list, just made it on the list. So today, the fastest computer is listed here at 1.19 exaflops, and the guy at the bottom of the list is at 1.87 petaflops. So that's sort of think of it as the spread of supercomputing over time. And the fastest computer back in 1993 was a machine at Los Alamos National Laboratory in New Mexico. It's a Department of Energy laboratory, and they used that machine to do nuclear weapon design. And that computer produced that 60 gigaflop rate of execution on the benchmark. The laptop I'm using up here is a sophisticated device, I have to say. I can run the benchmark on it, and I get 426 gigaflops out of this machine that I use casually to read email and to give talks. And I use it on a plane for 12 hours. It's an amazing device. 426 gigaflops, that would have been on the list not too long ago. It would have been faster than that machine at Los Alamos, and we use things like that as in a very casual way. This is the list of the top 10 supercomputers today. So the way to read this list is, this is number 1. This is a machine at the Department of Energy laboratory called Oak Ridge National Laboratory. It's a computer called Frontier. It's integrated by HPE. So HPE doesn't make chips. What they do is they take chips and they put them together in a box. So in this case, they took chips from AMD, CPUs and GPUs, put them together in a box, and put them together with a high-speed interconnect that came from Cray Research. Cray Research used to make computers. They don't anymore. In fact, HPE purchased them. So this machine has 8.6 cores in it. So that's the number of cores that were used to run the benchmark. And it ran the benchmark and produced a rate of execution of 1.194. And that's 71% of the theoretical peak performance. The theoretical peak performance is a paper and pencil calculation. What's the frequency? How many cores do you have? Multiply all that together, and that gives you a number that we think of as the theoretical peak. And then when you run an application on it, your performance is going to be less than that. In this case, it's 71% less than the theoretical peak performance. And then there's something called the power that's used. So this is the power consumed under load. So it's a rate, and under load, that computer is consuming roughly 23 megawatts of power. So what's a megawatt? Well, in Tennessee, where I live, if I used at my house 1 megawatt, and I used it for 1 year, I would get a bill from the electric company for $1 million. So that's a megawatt year. So this computer cost about $23 million just to turn it on. Of course, it for the year. This machine costs $600 million, so that has to be put in context. The last column is the number of gigaflops per watt. So that's your efficiency. You want that number to be as high as possible, and they're up to 52 gigaflops per watt. You could scan down the list here and see the machines. There are 6 machines in the US on the top 10, 1 in Japan, 1 in Finland, 1 in Italy and Spain. China used to have some machines on the top 10, but China is an interesting situation. They used to have 2 machines, in fact, on the top 10 the last time the list came out. This time those machines have dropped, as older machines always do, drop down further in the list, so they're not represented in the top 10. So this is number 1. This machine has 2 exaflops of peak performance. So that's, again, the theoretical peak. And it uses AMD processors. It has an AMD chip, and it has 4 AMD GPUs. That makes up a node on this machine. And then that node gets replicated and fills up a room about the size of 2 tennis courts. That machine has 9,400 nodes in it. And again, if you're going to program this machine at scale, you have to orchestrate message passing between those nodes. So you have to orchestrate between 9,000 nodes, sending and receiving information across that. But the interesting thing is it has the ability to do 16-bit floating point arithmetic. Using 16-bit arithmetic, the execution peak rate is at 11 exaflops. So you see the advantage if you can use short precision of using it. And that's where machine learning comes in, because they only need short precision. But 99% of the performance for this machine is coming from the GPUs. So again, if you're going to use this machine, you had better be doing something with those GPUs. So here's the chart again of the top 10 machines on the list. We reached a teraflop, 10 to the 12 operations, back in 1997 with a machine at Sandia National Lab. And then 11 years later, we got 3 orders of magnitude improvement in the supercomputer. That was a machine at Los Alamos National Lab called Roadrunner. So it was 11 years later, 10 to the 15 operations, and now we're at exascale. And it took 14 years to get 3 orders of magnitude. So it's taking longer to get to higher levels of performance. And if we look at that list, we see that, and do a projection, what's going to happen in the future. The projection says it's going to take 8 years to get 1 order of magnitude increase. So 10 exaflops at 64-bit computations will take much longer than we've seen in the past. And to get the zettaflop, which is the next 3 orders of magnitude beyond exa, it's going to take a lot longer and may extend that for many, many years. So this is the list of the top 500 computers ranked. We see the list here. So there are 500 dots here. That's the number 1 computer. That's number 2, 3, and that's number 500. So you see that long tail associated with the machines. So in some sense, if I was doing this over again, I don't think I would have 500 computers. So many of those computers are not doing scientific computation. If we take a look at 50 computers, maybe that would be enough. So that's a much, much shorter list and gets a better representation in terms of large-scale scientific computing. There's rumored to be 2 or 3 exascale computers in China, but they haven't submitted the results. So the question is, why haven't they submitted the results? So you have to run the benchmark, and then you have to send the results to the top 500 website. And it's a geopolitical issue. China's concerned that the US may impose further restrictions if they brag about their high-performance computing systems. We know they exist. I've talked to the people in China about those machines. And so China's really slowed down the submission of the top 500 list. This is what the list looked like in 2022. 162 machines. Of the 500 machines, 162 were in China, and 125 were in the US. The most recent list that we have shows a different story. It says that US has 161 machines and China has 104. So China's reduced the number of machines that it's submitting. In fact, I think we only had one submission from China in this most recent list of the top 500, one new machine listed. So they've really taken this business about US impact quite seriously. But China is still the top producer, the top maker of supercomputers. So companies like Lenovo, Inspur, Sugun, NUDT, Huawei, they're the companies that make supercomputers and sell them. Some of them sell them worldwide. So there are, for instance, Lenovo supercomputers in the US that people have purchased. So this LINPACK benchmark that I've been talking about that the top 500 is based on was done a long time ago. And it was done at a time when floating point operations were very expensive compared to anything else that you did on the any computer. And today that's not the case. But the benchmark has a number of positive features. It's easy to understand. It's easy to run. It shows trends that we have. And as I mentioned, a lot has changed since 1979. So the LINPACK performance is no longer a strong correlation of what real application performance will do on the high performance machines. So if you design a supercomputer to do well on this benchmark, most likely it's not going to do very well on your applications, is what I'm trying to say. So designing something for this benchmark specifically is not going to be the thing that you should be doing. Today's high performance machines really do work in a number of areas. I showed a list of 21 applications that the Department of Energy was interested in. They're used for climate modeling, for combustion, for nuclear reactor analysis, for fusion, for stockpiled stewardship, for materials design. They're used for accelerators and trying to get them to work correctly. So usually there's a three-dimensional partial differential equation that's being used in the simulation, and that three-dimensional partial differential equation gives rise, when you discretize that system, it gives rise to another system of linear equations. But the matrix is not dense. The matrix is sparse. And we have other techniques for working on sparse matrices. So what we'd like to do is to come up with a benchmark that looks at that problem and tries to understand what the performance is for that problem. So that problem, we come up with a benchmark. It's called HPCG. The matrix that we have has a structure which looks something like this. It's sparse, many zeros in it, and it has this diagonal structure around the matrix. And we have techniques that we use to solve it. We don't have direct techniques, as is Gaussian elimination with partial pivoting. We use an iterative technique. And the iterative technique starts with an approximation. It tries to refine that approximation and ultimately converges to the solution to the problem if we're lucky. And we put together a benchmark that works on symmetric positive definite matrices. It uses the conjugate gradients algorithm. There's a preconditioner associated with it. And this is the results of that benchmark. So this is a benchmark now which is reordering things slightly. What I've done here is to list the top 10 machines for this benchmark. So the number one machine is the machine in Japan, the Riken supercomputer. And that's the performance for LINPACK. So that's doing the dense computation. And this is the performance for doing the sparse computation, the problem which is more like the real applications running on this machine. And the thing I want to point to is the last column. That's the fraction of peak performance that we're achieving for this particular application, for doing the sparse application. We're getting, in the best case, numbers that are lower than 6%. 6% of the theoretical peak performance. For the LINPACK benchmark, we're getting around 75 to 80% of the theoretical peak performance. Here we're getting at something less than, and the number one machine is getting 3% of the theoretical peak. And those machines, the machine at Oak Ridge National Lab is getting less than 1% of the theoretical peak. That's an incredible situation. Don't tell anybody, because we'll get in trouble. Less than 1% of the theoretical peak performance we're seeing on these computers here for applications which are more typical of the applications we see on these computers. So that's a warning sign. So think about a race car. If you buy a race car that can go 200 kilometers per hour and you're only getting 2 kilometers per hour, you're going to be pretty disappointed in that race car. And that's sort of the situation that we see here. The best computer, the best in terms of ratio between its theoretical peak, is the guy who's in number 10. He gets about 5.5% of the theoretical peak. That's a computer that has a vector architecture at its core. So it's a very simple architecture using vector instructions. And it has a lot of bandwidth associated with it. So data movement's very expensive. That computer has very good data movement. So recently we've seen AI and machine learning take off. And they've been around for a long time, so what caused that to happen now? So we have the flood of data that can be used for training, scooping up all the internet and basically using parts of that for the training around machine learning. We have this increased computational power that's coming to us because of the GPUs that we have available. We have this increased progress that's been made in terms of the algorithms that have been used for machine learning, in terms of the theory and the actual algorithms that are used by people. And we have the support from industry to really drive the field forward and make it useful. So machine learning, deep learning needs matrix computation. So linear algebra is part of the scene here. They have small, dense matrix computations to do, very small, on the order of 3 by 3 or 5 by 5 dense matrix computations, but many, many of them. And those can be effectively done using the GPUs, and that's one reason why they're so popular. And we see this whole group of new companies springing up to develop hardware that gets used in this area here. So this is just a small list of companies that have designed their own hardware, selling it in some cases, to solve this machine learning problem. And it reminds me of the days when parallel computing was starting in the at the turn of the century, when we had a lot of companies that were getting in using those killer micros to develop high-performance computers. Those companies, most of them either were bought by other companies or went out of business because they couldn't support themselves. And I'm pretty sure that most of these companies will fade away in a similar vein to fall out. So we have floating point arithmetic, and it comes in different flavors. So there's a standard, an IEEE standard. One of my colleagues, Velvel Kahan at Berkeley, got a Turing Award for his work in developing this standard. So it's an IEEE standard for doing floating point. There's a standard which talks about 128-bit arithmetic. Not many people implement that in hardware. It's always done in software. We have 64-bit floating point arithmetic. So what we're looking at here is there are 11 bits for the exponent and 52 bits for the fraction, or for the precision of the numbers we're going to operate on. And then going down the list, there's 32-bit floating point and 16-bit floating point. The standard has a floating point representation which has 5 bits for the exponent and 10 bits for the fraction. 5 bits for the exponent says that you have a very short dynamic range associated with your numbers, and it causes you to do scaling in order to fit within that range. So Google says we're not going to do that. Google says we're going to have bfloat 16, which basically has the same dynamic range as single precision, 32-bit arithmetic, but less precision associated with it. And again, machine learning doesn't need precision, so they can get away with that. And we even see companies coming up with hardware that does 8-bit floating point arithmetic. So NVIDIA has 8-bit floating point. They make up their own format for doing that, and it's now in use. So the question is, can we use that shorter precision in our numerical computations? So what we want to do is to exploit the fact that we have this very fast floating point arithmetic, but with short precision. And from the standpoint of a numerical guy, we want to see if we can use that to get an approximation and then do something to enhance the precision and maybe get to the same precision that we got with the 64-bit. So the idea is to structure things in a way that we can do that. So exploit the fact that we have 16-bit arithmetic as long as possible, do the bulk of the computation in 16-bit arithmetic, and then refine the solution using some mathematical techniques to correct it up to 64-bit. So that's the goal of the operation. So this example here uses a dense matrix computation. It uses Gaussian elimination. We factor a matrix. When we factor a matrix, we do order n cubed operations in the factorization. And then we use those factors to solve the system of equations. Using the factorization to solve the system cost n squared operations. The bulk of the work is in factoring the matrix. The order n squared is used to do a solution. So the idea here is to factor the matrix in short precision, get an approximate factorization, come up with an approximate solution, and then use some mathematical techniques to build back the solution to 64-bit accuracy. And the technique that's used is similar to, in fact it is, Newton's method. So we get an approximation, we iterate using Newton's method on the problem, and build back the solution to 64-bit accuracy. That's the goal. So the bulk of the work, the order n cubed work, is in lower precision, and then all the other work that's done is only order n squared. Some of that work gets done in 64-bit operations, and some of it gets used in lower precision. So there's an algorithm that we've used. It's a classical algorithm called iterative refinement for solutions of equations. Again, it's Newton's method under the covers. And a number of improvements have been made quite recently in this. My colleague at Manchester, Nick Hyam and Aaron Carson, said that we can solve the innermost iteration there by using an iterative technique, not by solving it directly, using GMRes. GMRes is a very powerful tool for solving systems of equations. It's usually used for sparse problems. In this context, we use it for dense computation, and we have a very good preconditioner. The lower precision LU factorization is used, and we have an approximate solution, and this technique uses just a few iterations of GMRes to converge to a 64-bit accurate solution. So we have a very good story to tell in terms of our time to solution and our overall effect. So this is running that algorithm on a accelerator, an NVIDIA accelerator. And the curve here is showing us increasing the matrix size, solving a bigger problem. And we're looking at the rate of execution. So the rate of execution here, in this context, you should think of it as the time to solution, and in terms of the relative ratios of things. So that red line is just solving the problem using 64-bit. Forget about the iterative stuff I've talked about. That's the rate of execution that we see for that algorithm. If we implement that iterative refinement technique using GMRes, now doing the inner parts in 32-bit arithmetic, we end up with a time to solution. So the ratio here is based on the time to solution, which is effectively a factor of 2. So using the 32-bit arithmetic, getting the same accuracy as we did with the red curve, I end up with a solution method which is twice as fast using that iterative method. So we get an approximation in 32-bit, refine it, coming up with a solution that's good to 64 bits, and we do it in half the time as we did with the other. Using 16-bit arithmetic, we do that same algorithm, only now getting the approximation using 16-bit. And again, we get that bump in terms of a factor of 2 in terms of performance on this machine. And we can use another technique that's available on the NVIDIA chip using their CUDA cores and getting things much faster than that. So we end up with something which is basically a 4-time increase in performance, time to solution, which gets exactly the same accuracy as we did with the traditional method of using 64-bit. So that's a good story, and there's a benchmark story that goes along with this as well. So we have another benchmark which implements that algorithm on problems, doing that implementation, getting the same accuracy as we did before, and we're measuring the time to solution. So in this case, the interesting thing to look at here is not so much the ordering, but the speed up that we see. So this is, we're looking at, if we take a look at this column here, we're looking at a situation where we have an 8-time enhancement in terms of the, so that column represents the rate of execution for doing the traditional way, 64-bit. The last column represents the speed up that we see associated with this mathematical technique for enhancing the performance using mixed precision to get us to that point. Okay, we've come to the conclusion. So this is my next to last, my last slide. So what we see is the hardware for high-performance computing is constantly changing. We've gone from a situation where vector computers were the dominant situation to a situation where distributed computing in the form of parallel processing was the way in which things were done. And then we went to accelerators to boost the performance using GPUs. And now we're looking at maybe even using mixed precision to help the story along. We've seen these three computer revolutions. Although I've only talked about high-performance computing and deep learning, there's also this issue going on with edge computing and the use of AI to help with that. Algorithms and software usually follow the hardware. So the model that's been used is that the hardware guys put together a machine based on commodity processors, based on commodity interconnect. And that's done in scientific computing because we're trying to get to the lowest cost for the machine with the highest performance. And we're not thinking about how easy it is to use. So that machine is put together and they throw it over the fence, and the algorithm people, the application people, and the software guys struggle for the next few years to develop their applications that can work well on that machine. And after 4 or 5 years, we finally are in a situation where we're using that machine quite effectively, and then a new machine gets thrown over the fence, and we have to start that process over again. So that's sort of the mode that we're in. So there really is plenty of room at the top. This is a riff on Feynman's story. There was an interesting paper published a couple of years ago in Science by Charles Lyserson and his friends. It talks about some of the struggles that we encounter using these machines and ways in which we can use algorithms and software to overcome those struggles. So as Feynman said, there's plenty of room at the bottom. They're claiming there's plenty of room at the top, especially when we only see 3% of the theoretical peak that we're achieving. There's a lot of room there for improvement if we use algorithms and better use of our methods to effectively come about with the solution. So I'm going to stop there. I'd be happy to answer any questions. Thank you for your attention.
Thank you, Professor Dongarra, for that insightful and thought-provoking lecture. Now, we will be moving on to the question and answer session facilitated by Professor Jar Xiaohua, Head Department of Computer Science. Jar Xiaohua, please. For the Q&A session, please raise your hand to ask a question, wait for the microphone, state your name and organization before posing your question. Thank you.
Okay, questions? Yeah.
First of all, thanks for the very entertaining talk. So my name is Minghua Chen. I came from School of Data Science at CTU. I think you present the history and the current status of presenting benchmark benchmark criterion for ranking the high-performance computing. I think that, but there is under standard architecture, there is new trend of using quantum computer as a high-performance computing. I'm wondering, can you share some light on, what kind of benchmarks should we use to rank them?
So the question relates to quantum computing and what can we do to maybe to benchmark quantum computing. That's right. Quantum computing, it's getting a lot of hype and maybe too much hype in terms of its capabilities. So there's only really a handful of algorithms that are really built for quantum computers. I don't see quantum computers as replacing our standard computers in the near future. Probably won't happen in my lifetime. We really have to get down to getting error-correcting chips, fault-tolerant in terms of the qubits, and then also we have to get down to gate-level quantum devices, and we haven't quite got to that point. But a lot of companies are making quantum computers and are happy to sell you one. So I think we have to be a little bit careful about the scope at which we'll be able to use them. But I think it's an interesting research area, so we should invest in that. So that's a good area for developing, trying to come up with better algorithms, coming up with some algorithms that deal with quantum computers in some way. I would say that's a ripe area if somebody wants to go in for it, but I would be cautious of the hype that we see today for quantum computing. Quantum computers are going to, in my mind, be sort of like an accelerator. So we'll use them as a special purpose device along with other devices that we have on our supercomputers. So if we can invoke a quantum algorithm, we probably should buy a quantum machine and put it together with our conventional supercomputer and then use it to do the problem that it's good at doing. We wouldn't use it to solve systems of linear equations. It doesn't make any sense unless somebody comes up with really an impressive algorithm. I know there are some algorithms that have been developed, but I don't see those as being practical.
Good. Yeah, next question. Yeah.
Oh, thank you. I think your talk is really amazing and excellent. And I come from the computer science, and I wonder your opinions about the future direction of the architecture is towards more domain-specific accelerators or the stronger, the general purpose processor like wider vector unit and so on. So if it's towards the domain-specific accelerators, and how can we, among this newly proposed accelerator, how can we evaluate the potential or the benefits it can bring to the general computations instead of that specific applications? Thank you.
So this is an important area. If we have an important enough problem that needs a computational solution, maybe we should build a special purpose machine for doing that. And there have been such machines built. They're very successful for solving that one problem. And if that's an important problem, then we should go at that. We should go at that problem. My colleague D.K. Shaw builds a special purpose machine for doing some of his computations, and it's very much more efficient than using a conventional computer. But it's costly to do that, and it only does that one problem. So if your problem's important enough, then let's do it. We think about building large scientific instruments, the Large Hadron Collider, or the gravitational wave machine, or the square kilometer array. Those are sophisticated scientific instruments used to solve a one-off kind of problem, and we spend billions of dollars on that equipment to do that because it's important. If the problem is important enough, then we should build a specialized processor to do that. So that I think is a reasonable approach to the problem. If it's general purpose, then we're stuck with the situation that we have. And as I said, the commercial guys are building their own hardware because they have the resources. They have so much resources. They're exothermic in terms of the money they have. They have so much money that they can invest in these hardware parts where the scientific is endothermic. We're really struggling to put together the funding that's needed for our machines.
Good. Next question.
The guy with the black hat back there.
Yeah, to the back.
Hi, Jack.
Hey, is that Tony?
Yep. So you mentioned about GPUs, right? So I think a lot of these machines are now more GPU dominated than CPU. So will it happen one day that we'll have mostly GPUs? Because it's not just the performance, it's like everybody believes that AI will take over everything. So for example, for your application, climate, weather forecasting, AI can do all that, right, supposedly? Well, so is that true? I like your opinion. Thank you.
So, so companies that make GPUs are making a lot of money today. As we saw, the worth of NVIDIA is at $1 trillion. Incredible story that they have. In fact, in some sense, they're almost priced themselves out of the scientific computing market. So the cost for NVIDIA parts is so high today because the AI guys are willing to pay for those parts and use them in their applications. It makes them unaffordable to the general scientific computing groups in most cases. But other companies are making the GPUs as well. So, so I think, so getting to your question about AI and GPUs, so it's not going to be the thing that solves the problem. It's not going to be, AI is not going to give us the climate forecast. It's going to be the thing that helps us with the climate forecast. So today, almost all scientific papers that we see that does scientific computation has some aspect of AI going into it, machine learning in it. to help with the computation. So it's a helper. It's a tremendous tool that we're going to be using to help us in getting to the solution faster. That's sort of my take on machine learning. So it's something we should understand and use. It's something that will help us get to the solution, but it's not going to be the thing that will, it's not going to be the thing that will void all of the Newton's equations and all the other mathematics that we have. It's still going to be used in conjunction with that to drive a solution to its conclusion. So it's an important tool. We should understand how to use it. It's something that, as a computational scientist, we should have in our toolbox and draw on when needed to help us in solving the problems.
Yeah, I see that student.
Thanks for the nice talk. So I'm from Department of Physics. So I have two questions. One is a basic one. So you mentioned your benchmark is to ask the computer to solve some dense matrix problem. And you also mentioned you care about the precision of the answer. So I was wondering, how do you get to the correct answer given your matrix is such big? Like, how do you know if any computer gives you the right answer? And second question is, I'm curious, what will happen for this 800 talent after their project finished? Like, what will happen for them next year?
Yeah, what happens to all those guys? So let me answer the last question first. So 800 people are now looking for a job. And I view this as a shock to my group as well. So in Tennessee, I have a group of researchers who have been working on the various software and algorithms for the past 30-some years. And they're well trained, they understand how to do this, they know about high performance computing, and now funding is gone. So I don't have funding to keep them alive. That is to say, they're going to be looking for a job, and they're looking for a job today, and where are they going? They're going to companies. So who's the beneficiary of this? Not the Department of Energy. They just provided 800 very talented people to companies like Amazon, Facebook, Google, Microsoft, and so on down the line, the computer vendors. So they became, DOE has become basically a minor league for the major leagues. And at the university, that's what we do. We train people and we send them off to other things. I'm happy with that story, but DOE should not be doing that. We lost a tremendous talent pool. Okay, so that's the second question you asked. The first question you asked, how do you know you got the right answer? That's an important question. In linear algebra, there are ways that we know we get the right answer. You can compute a residual. If you have a stable algorithm, it's going to produce something which that residual is meaningful, and we can say that our answer is correct up to this number of bits. If the problem is well conditioned, we can make that assessment. Other areas, it's not so easy to do, and we need some intuition about what the answer should be. So if you do a computation that takes days, months, you want to be sure that you're getting the right answer. Otherwise, you're just churning numbers, and that's spending a lot of time heating up something and not really getting it. So we need some intuition about what the answer should look like, and hopefully be on the right track to that. And that'll have to depend on the application area. I can't give you the intuition for each problem. But in linear algebra, there's we have some very well-defined ideas about what we know about the answer, what the correct answer is dependent on, and we could see, in fact, if we're doing that. So the computations for the benchmark is just as an example. It takes about 4 or 5 hours to run that benchmark on the fastest computer, 4 or 5 hours. So doing a lot of computations, and at the end, I can see if you got the right answer or not. So it's a very simple test. So that benchmark has a lot of value in terms of just shaking down a machine, making sure that the machine is working correctly, because I know what the answer should be. And it's used in just that way when people are bringing up a new machine, to verify that the hardware is doing the right thing and the software underlying that is correct or working right.
Good. Next question. Yeah, Stella, please.
Thank you, Jack. Very nice talk. I work at the bottom, so I do hardware. I agree that there's plenty of room at the top. I just wonder how much room do we still have at the bottom? I know that there's a limit for scaling and continue to scale down. I just wonder what you think about as we keep pushing it down to the bottom.
Right. So, yeah, Moore's Law is not over. That's one thing. Moore's Law is still with us. It's slowing down, so we don't get that same effect that we did of doubling the number of gates every, whatever Gordon said, 12, 18 months was the trend. But it's still improving. It's still getting there. You know, with high-performance computing, we've gone through trends. You know, I mentioned scalar to vector, vector to parallel to using GPUs. So we're waiting for the next big thing to happen. And I don't know what that next big thing is. Maybe it's using mixed precision. So we get the boost in terms of things by using short precision in our computations. Or maybe some other architectural trend will take over and you know, help us beyond GPUs to get to that point. You know, we see today that you know, the way the GPU and the CPU is organized is they're two separate devices, and we have to send information between those devices. So that's changing. The hardware guys are merging those two things, so they become a unit, and the transmission of data is not done through a very slow mechanism. It's done through much faster mechanisms, and that will help or boost the performance. In fact, AMD with the machine, one of the 3 machines I talked about for the next exascale machine, that machine will be using AMD's chip, which actually does that fusion of the CPU and the GPU into a single unit. So maybe that'll help. The other thing from the hardware standpoint is, you know, today we're in a situation where we have things called chiplets that we can use. So chiplets are small components which sit on the chip itself, and those chiplets can be designed, and there's an interface which is a standard. So we can think about interfacing. So let's say that FFTs were critical to your application. We could design a chiplet that did FFTs and put it on the chip so it ran real fast. Or we could think about singular value decomposition. If that was something that was important to your application, designing the chiplet that did it and put it on the chip itself. So it ran very fast at hardware levels, not software that slows things down by orders of magnitude. So, you know, maybe there are ways of maneuvering there, but it costs, I mean, so now what does it cost to design those chiplets and to produce a chip with those components? That's something people have to figure out. And again, we're endothermic. So the scientific area doesn't have the funds to really go out and build very expensive things from scratch, which is what the other guys, the hyperscalers, are capable, the cloud vendors are capable of doing. I don't know if that helped.
Yeah, good. I saw, that in red, that young man.
Yeah, so my question is, you know, today many people use GPUs to do AIs, but GPU is really originally designed to process graphics, and nowadays it is more and more suitable for AI. But if people design the processors from the ground up to do AI, would it be better?
Yes. I had a slide which showed, I don't know, 20 different companies that are building chips specifically for AI. And those chips can do the training very efficiently, let's say, and help with other components of that. So they do it very, very fast. They're designed for that. The chip that comes to mind is Cerebras, is a company that makes a chip. The chip is a big chip. So it's a big chip. You know, roughly 1/3 of a meter sort of area for the chip itself. So it's an enormous chip. They have an architecture which is more data flow than anything else. So it's a different way of programming that you have to do to effectively utilize it. But you know, it's an interesting architectural feature that they have on their chip, and they've been quite successful in terms of selling that to the community. So I think there are special purpose machines that are being developed for AI applications, and we'll see what the shakeout is. So the shakeout will happen. Companies will go out of business, but the strong ones, or the ones that are lucky, will survive, and we'll see more of them in the future. So I would say that that's an important thing. I just hope that they have 64-bit arithmetic still, rather than to rely on 16-bit only. The problem with Cerebras is they don't have 64-bit. They have 32-bit is what they provide in the hardware itself.
Good. Any more questions? Yeah. Okay. Yeah.
Yeah, Ronny Ramler from Radon Institute in Austria. Your last takeaway point, the algorithm software advances follow hardware. I'm not so really sure about that. I mean, many simulation systems have been developed over, let's say, several decades, and they contain, well, let's say, partly outdated software algorithms and so on, and now they are running on high-performance computers. So it's kind of, like your laptop and your email program. So we are running software that is old and outdated on these machines. So shouldn't we put actually a lot of more energy into the algorithm development?
I agree 100% with that. I think that the algorithm development is the right direction to investigate. It's a frightening situation for applications people when you have a legacy application which is 20 or 30 years old, and the people who wrote that software are no longer with us. And now that software is hard to modify. So you make small changes to it, and the thing just broke, and now you don't know how to fix it. So you don't make changes to it. So you suffer the consequences of that in terms of the performance that we see. Again, there's plenty of room at the top in terms of improving that. If we could make the changes to that software and to the algorithms that are there and bring them up to speed in some sense with today's techniques on the modern hardware. But doing that from a standpoint of legacy software where the original people who designed it are no longer around to interpret what they've put together is a frightening thought.
Yeah, we have a okay, yeah.
Thank you for the great talk. So my question is, in one of your slides, you showed that oftentimes the computational resources are over provision. It's very expensive and energy consuming. So I wonder what's your opinion regards, like, how can we appropriately use those computational resources so it's faster enough, but we're not wasting too much energy? Like, is it always necessary to have this highest frequency? If no, how do we find the balance point and so forth? Yeah.
Right. So, so I'm not sure how to answer or interpret the question. So we don't have to run the computer at the frequency. We could detune it. Is one way of doing the situation. So run it slower, and have the communication still run at the same speed. So the CPU is not running as fast. And maybe as a result of that, we can get by with less power consumption. So that's one way to do it, is to detune the CPUs, to make them run slower, but have the communication run at the same rate. We're over-provisioned in terms of the floating point capability anyway, so maybe that's a reasonable situation. There are many aspects of the machine, though, that consume power. Memory is there, the network is there, and of course the CPU is there to do that as well. And they all share in the power budget. So we got to be a little bit careful how we adjust things. The machine at Argonne, in fact, they're thinking of detuning, running it slower because of the power requirements of the room. They don't have enough power in the room to run the machine perhaps at the full rate that it's capable of. And they understand that nobody's going to get the full performance, but that's okay. So those are potential solutions. Not solutions, but ways to help with that issue.
Okay, that young man, yeah.
Thanks for your presentation. It's like very excellent. So I'm Don, and I'm from Mechanical Engineering Department. So I got one question. For the high performance computation, like this industry area, should people devote more effort to the software side or the hardware side? Because for example, the NVIDIA, the company every year they will just release some new devices like the H100 and the A100, things like that. Every year the device got 2 times power, is 2 times more powerful than the old one. So it's like pretty quick, and you have to change it. And also another thing that you said, the transportation of the data from the device to the host to device is like takes a lot of time. Now they have the NVLink, I think, so that saves you a lot of time. So for the people, they are like doing the software things. Well, actually, you don't have to like come up with some like a complex algorithm to cope that kind of things with the hardware like this. So should we devote more efforts to the hardware or software? Yeah, thanks.
Well, I'm a software guy, so you know how I'm going to answer your question. You know, I think, so we're always striving for getting higher performance, and we're driven to higher performance because we want the applications to run faster so we can do more, and we want to get greater fidelity, so we need bigger machines that run faster. Those are the 2 main reasons why supercomputers are used. And you know, from my standpoint, I think many applications people, you know, we would like to exploit the machine as best as we can, and that says that we're given a machine, that machine's going to be around for a number of years. It doesn't change every year. The hardware can change every year, but we make an investment that's going to be there for 5 years. And that 5 years says now we have to implement something. And now the algorithms and the software guys have to do something. And they usually have to work hard to effectively use that new hardware that just came on the scene. And they do that for 5 years, and then a new machine gets thrown over the fence, and we start over again. So it's a good way to have a job for life and improving the software and algorithms for these machines.
Okay, good. Yeah, I think we are running out of time, and I will take the advantage to ask the last question for myself. Yeah, this question is on behalf of many young PhD students. So if I'm a young student and I would like to do research in this area of high performance computing, what are the research topics you would suggest to this student, and what are the advice you would give for this student?
Yeah, so what advice would I give students? Okay, so I'll answer that part first. So I would say follow something you feel passionate about. You know, follow your passion. Get something that you're really interested in and follow it. Do that job. You should aim high. Don't go for the simple problems. Aim for something that's challenging, that you could work on and get something really that other people would think is important for you. You should expect to fail. It's a research problem. If you didn't fail, it wouldn't be called research. It would be called engineering or something. So if you're involved in sorry, engineers. I'm an engineer. Wait a second, I didn't mean to insult you all. That's a joke. Just take it that way. Don't throw anything up here. So it's a research problem, so you should expect to fail. It's an engineering problem, you should expect to fail. Okay, so it's a way in which we can effectively, you have to go through a process of learning and overcoming and learning from your mistakes, I guess is really what I'm trying to say. And the 4th thing I would advocate is, talk to people, network with people. Bounce your ideas off of other people. Don't be afraid to tell them what you're thinking about. They're not going to steal your ideas. Really interact with them. I've had tremendous colleagues throughout my career, and I respect them and they respect me, I hope. And we've talked about many, many issues, and I've learned so much from them along the way. So those are the 4 things I would recommend. And the other part of your question was?
Well, yeah, I think you already answered both part.
Okay.
Yeah. Due to the time limit, let's thank Professor Jack Dongarra. Thank you.
Thank you, Professor Zhao, and for hosting the Q&A session, and thank you, Professor Dongarra, for answering the questions from the audience. Please remain on stage as we take a group photo. May we invite Professor Wei Kuo, Professor Chi Chan, Professor Raymond Chan, and Professor Stella Pang onto the stage.
I also invite the former UST President Tony Chan to come up to take a picture with us.
Thank you so much. Distinguished guests, please be seated. Ladies and gentlemen, this concludes the WACOR Distinguished Lecture. We hope you found today's event fruitful and engaging. Thank you for your presence. Have a lovely evening.